Welcome to ISL-enabled Virtual Lab of CSIR.
The starting point of any CFD simulation is grid generation in the fluid region within a certain boundary around the existing CAD model of the object under investigation. Grid generation is a process of generating discrete points around the object based on certain requirements. The collection of those points connected by lines is called a grid. The fluid flow governing equations are then solved at those grid points for getting all the flow variables such as pressure, velocity, density and temperature. Later, the behavior of flow is analyzed through various post-processing methods by using the available solution in the flow field. The details of a sample grid generated to study the flow over an aircraft through the CFD technique is shown now. Flow field generated with unstructured grid around the aircraft is shown now. Cylindrical far field 500 meters long and 150 meters in diameter is considered. The volume of the flow field is approximately 1 lakh times the volume of the aircraft and has approximately 50 million grid points. The grid density increases from the far field towards the aircraft for capturing the rapid changes in the flow variables better. For the sake of clarity, grid points inside the volume are not shown. Now, a denser block of grid around the aircraft can be seen. Upon further zooming, aircraft can be seen in the interior of the flow field. The number of points on the aircraft must be large enough to accurately model its surface curvature and to capture the flow details to a satisfactory level. As the number of points in the flow field increases, so does the accuracy. At the same time, the time taken to solve the flow problem also increases. The grid near the surface is intended to capture the boundary layer and is very fine in the normal direction to the aircraft surface. Only if the grid is fine, the rapid changes in the very thin boundary layer around the aircraft can be captured accurately.
Once the grid is ready, fluid flow governing equations are solved at those grid points for getting all the flow variables, for example, pressure, velocity, density, temperature, etc. Later, the flow can be visualized through various post-processing methods by using the solution available at all grid points. One such flow field visualization with a moving slice is shown now. A plane is used to show the flow field by moving it over the aircraft in the flow domain. But in the video, visually it is shown as the aircraft is passing over the plane. The plane and aircraft are colored with pressure. Blue color indicates low pressure and red color indicates high pressure. Even before the aircraft reaches the plane, pressure started increasing because of the influence of aircraft. Pressure difference can be seen clearly between upper and lower surfaces of the aircraft, which is the cause of lift. But major part is contributed by the wings. There is low pressure region in blue color at wingtips because of the presence wingtip vortices like whirlpool. Wingtip vortices of big aircrafts have enough strength to destabilize small aircrafts. Hence, enough gap is maintained in between takeoff of two aircrafts. Pressure difference between the upper and lower surface of the horizontal tail can also be seen. As there is no side slip, the flow over vertical tail is symmetric. Generally, horizontal tail and vertical tail are useful for controlling the aircraft. Even the aircraft moved far away from the plane, still its impact can be seen. By using the solution in the flow field, real feel of airflow can be shown through plotting streamlines over the aircraft. In this video, the streamlines starting from different levels are shown to visualize the flow. Streamlines are colored with velocity. Blue color indicates minimum velocity and red color indicates maximum velocity. First set of streamlines are passing underneath the aircraft. As the streamlines proceeds towards the aircraft, they turn into blue because of reduction in velocity towards stagnation point, where pressure is maximum. As the streamlines proceeds on the wing, lower surface velocity increases. In the wake of the wing, velocity is very less. Streamlines are now starting from higher level compared to first set. The flow behavior is similar until streamlines enters into wing wake. Few streamlines are now passing over the upper surface of horizontal tail as the aircraft is at 18-degree angle of attack. Now, streamlines are originating from next higher level. Few streamlines are passing over the upper surface of the wing with maximum velocity at leading edge. Very few streamlines entered into recirculation zone are also visible. Curling of streamlines can be seen clearly at the wingtips because of wingtip vortices. Streamlines are now starting from still higher level. All the streamlines are now passing over the wing. The velocity of fluid in the wake is very less. Curling at wingtip can also be observed. Many such flow visualizations are possible through various post-processing techniques by using the fluid dynamic solution available in the flow field.